Alright, so now we want to define some features of the atom. The first one that you're going to need to know is the atomic mass. So the masses of atoms are, again, very, very small. And so we said that the mass of the protons and the neutrons are essentially one atomic mass unit, and that the electron's weight is very, very insignificant because it's almost 2,000 times lighter than the proton and the neutron weights. So the atomic mass is really going to be determined by how many protons and neutrons that the atom actually contains. And so this was actually developed based on the atomic mass of the carbon atom, which contains 6 protons and 6 neutrons. So the element carbon was used to provide the scale for all of the atomic masses. And so the atom of carbon was given or assigned an atomic mass unit of 12 exactly. So 12 atomic mass units because it contains 6 neutrons and 6 protons. And then all of the other atomic masses were assigned relative to the carbon atom. So atomic mass is given the letter A. So you will need to know this. So the big A stands for the atomic mass. It's going to be the sum of the protons plus the neutrons in the atom. So again, the protons and the neutrons are packed very close together into the nucleus. And if we think about the size and relative space within an atom, what we find is that most of the atom is taken up by empty space. So if we think about the relative sizes, we can use a baseball stadium for an example. If there was a pea, like a green pea that you would eat, sitting on the pitcher's mound in the middle of this stadium, that would be the size of the nucleus of the atom, and then the rest of the entire stadium would be the space that the electrons would float around the atom. So atoms are really made up mostly of empty space. There's a very dense core where the neutrons and the protons are held, and then all of the space around here where the electrons are orbiting, so where these negatively charged particles are spinning around. But they are very, very, very small in size and don't take up much space. Elements in their fundamental units or bases are neutral in charge. And so what that means is that the number of protons has to equal the number of electrons within an element. So if an element has 35 protons, like bromine does, it also has to have 35 electrons. They have to balance each other. So the charges have to end up being neutral. So the number of neutrons within an element can be different from that of protons or electrons because the neutrons are neutrally charged. So they don't have to balance anything. So our atomic number that is listed on the periodic table describes the number of protons within an element. Any element in its elemental state then also has that same number of electrons. But as we're thinking about the atomic structure and the atomic core, if we go back to our diagram here, the protons and the neutrons are going to make up the most stable part of the atom. It's very, very hard to break apart this part of the atom and get protons and neutrons to come off. That sometimes does happen when you have radioactive particles, but in their natural state, most elements do not decay, and the nucleus is very, very stable. The things that can change about the atoms when they come into contact with each other and they start forming bonds with one another is their number of electrons. And so we're going to see the rules that the electrons obey when they start to share electrons or donate electrons to other molecules, is that the number of electrons can actually differ within the atoms when they start forming compounds. But in their elemental form, everything has to be neutral, and so you have to have the same number of electrons and the same number of protons. So in our periodic table, the atomic number is given and the atomic mass is given. So the atomic number is called the Z number, and this refers to the number of protons that are present in that element. And so that's not going to differ. Anytime you have that number of protons, that's the element that you're going to have. So our atomic mass then is going to be a sum. It's going to be the number of protons plus the number of neutrons. So you're given the atomic mass and you're given the number of protons, you can easily calculate how many neutrons are going to be present as well. And you can do that by rounding. So you can see that this is not an exact number, and you would predict that the atomic mass should be an exact number. I mean, you're essentially adding 1 and 1 for every neutron and every proton. So we'll see why this number actually varies from a whole number when we start talking about isotopes. But for now, you can round up and you could say this is pretty close to 80. So if we said there's a mass, atomic mass of 80, and then we have 35 protons, if we subtract 35 from 80, we would get 45, and that's how many neutrons would be in this atom. So we already said that each element has its own unique symbol, and you've already started learning these. So the first letter is always capitalized, the second letter is always lowercase. So that's just review here. And then we also said that a few of the symbols come from their Latin names, such as natrium for sodium and plumbum for lead. So you can see some of the nomenclature is a little bit more difficult because it comes from their Latin terminology. And then we also said that the elements are not equal in their abundance on the Earth. Oxygen and silicon together constitute about 75% of the Earth's crust, for example. So all of the known elements then are housed on the periodic table. And we can see if we go through and we're looking at each of these different elements, again, the atomic number, or the Z number, is listed up here. That's the number of protons. And the atomic mass is listed down here, 10.81 in the case of boron. So if we round up to 11, subtract that from 5, we would predict that boron should have 6 neutrons in it. So it would have 6 neutrons and 5 protons. Carbon at 12 would have 6 protons and 6 neutrons. Nitrogen, 7 protons, 7 neutrons. Oxygen, almost at 16, 8 protons, 8 neutrons. So you can calculate the number of neutrons in any one of these elements by subtracting the number of protons from it. And then remember in their elemental states that the number of protons is going to also equal the number of electrons. So if we have elemental aluminum, it's going to have 13 protons, 13 electrons. This is very close to 27, so 27 minus 13 is going to be 14. So most of the aluminum should have 14 neutrons as well. So the diameter of a nucleus is very, very small. So we said in that interesting factoid that there are 3 times as many carbon atoms in a teaspoon of carbon than there is teaspoons full of water in the Atlantic Ocean. So that's a large number of atoms. And so when we start talking about atoms, we get into very, very, very small measurements. So the diameter of a nucleus is only about 10 to the minus 15 meters. So that's the length across here. And the diameter of the entire atom then is only about 10 to the minus 10 meters. So these are very, very small particles. And you can see that most of the space then in the atom is held up by empty space where the electrons are going to be spinning around this atom. So the structure of the atom then is determined by the interplay of these different forces. So we already said that opposite charges are going to attract each other. Like charges repel each other. So protons are going to repel one another because they're both positively charged. Electrons are going to repel each other because they're both negatively charged. And these are important relationships when we start thinking about how atoms interact with each other. The protons and the electrons are going to attract one another. So already this seems really strange because if we look at the structure of our atom, we can see in the nucleus the protons and the neutrons are all jammed together really, really closely. And so this is causing protons to be very, very close to each other. They normally wouldn't want to do that, right? Because protons are going to repel each other based on their charge. Since all protons are positively charged, you would predict that the protons should repel each other. So why don't they? Why are all the protons jammed together in the nucleus? And this is because there is a stronger force that's at play within the nucleus. So it overrides the electrical charge attraction that these molecules have for each other. And this is called the nuclear strong force. So the nuclear strong force is much stronger than the charge repellent between two protons that are positively charged. So even though those two protons want to repel each other based on their charge, this nuclear strong force helps keep the nucleus together. Those molecules in there will stay very tightly bound in the nucleus, and the nucleus is a very stable component of the atom. It rarely ever will break down. So the atomic number again is the Z number. It refers to the number of protons in each atom of the element. And all of the atoms of a particular element have the same number of protons in the nucleus. So when Dmitri Mendeleev started building his periodic table, he thought that the atoms were defined by their atomic mass, that the overall mass of the atom determined the properties of that atom. What Niels Bohr found is that it wasn't the mass that was the important component that defined an atom, but it was the number of protons that are present within the atom that help define what the element is. And so the atomic number becomes very important. So in effect, what Niels Bohr found was that the atomic number, or the Z number, is the important determinant for determining the elemental properties. So all atoms of a particular element have the same number of protons in the nucleus. The defining feature of an element is the number of protons that are contained within the nucleus. So again, the atoms are going to be neutral because the number of protons and the number of electrons are going to be the same in each atom of an element in its elemental form. And the atomic mass number is the total number of protons and neutrons within the atom. But what we're going to see is that for each element, the number of protons always has to be the same, but we're going to see that the number of neutrons can vary, and that you can have different types of atoms that make up a single element, but that the number of protons has to be the same within those atoms. And those guys are going to be called isotopes, and so that'll be the next area that we start to look at.